Hello, another quick video, because apparently I've already done this one. So, I did this problem a long time ago, I guess, but basically we are looking for a search insert position. This one's an easy problem on lead code, number 35, pretty simple. The only problem is that we have an O log n runtime complexity, which is the algorithm we had to look for. However, we are provided a sorted array of distinct integers and a target value that we're looking for. We want to return the index that it is located in if it exists inside of the list that we were given, or we want to return the index where it should be inserted if it is not in the list provided. So let's look at this case right here. We're looking for target 2. 2 is not in the list, so what we're going to do is we're going to insert it at position 1. This is going to be to the right of the smallest value, or the largest value less than the target. In this case right here, we have a target that's 5. 5 is right there. We're just going to look for it. 5 is at index 2, and that is the case here. And then we have target number 7. 7 is going to be inserted at index 4. This is because if we look at it, we have 1 or 0, 1, 2, 3. 7 is greater than all of the elements right here, so we want to insert it to the right of 6, which would be 4. So that's a little edge case where it's like, okay, we're inserting it at the end of the list, so we should increase the size of the list. It's not limited to just the size of the list, it can be one more than it. It's distinct and it's in ascending order. Since they're distinct, we don't have to worry about non-descending, it's just ascending. So, yeah, when I was solving this the first time, I also thought the same thing that I did now. Can't we just use binary search? Yes, we can. That's literally the part. It's literally just binary search. So what we're gonna do is we're just gonna do normal binary search. We're gonna return mid if we find the target. That's gonna give us the index where the target is found. Now the important thing is left is less than or equal to right. We're gonna do that condition, and when it fails, what this means is that the left has overtaken the right, and it's going to be 1 to the right of it. Right is going to be located on the largest number less than the target. So that means that left is going to be 1 more than that, aka the position that we want to store or to insert the target. So if this condition is never met, then the condition that will cause us to break out of the looping and not loop infinitely will be this one. And if that condition ever fails, we're just going to return the left index, and that is the location of the insertion that we're going to be doing. This allows us to keep the O of log n time complexity, because all we're doing is doing a normal binary search, and if it fails, then we just return the left index. It's simple. It's literally just one line difference from binary search. So yeah, and that's the solution. I did basically the same thing in C++, I'm pretty sure. Yep, basically same thing. Don't know what I was doing here. Oh, I remember this. I was like, oh, I had to look at the next one and then the previous one, and then I had to do all this stuff. No, it's more simple. You just do a normal binary search. But yeah, that's the problem. And I use else because while and an else, the else will always be triggered if you exit the while loop with this condition failing. If you break out of the loop or return from the loop, that the else statement will never run. And I thought it was just like, okay, well, that makes it clear that we're only doing this because that condition fails. I thought it was like nice to say explicitly that's happening, but I understand why you wouldn't want to do this.